Is yes, good, excellent. Thank you, Sergey. My talk is entitled Remote Sensing of High-Latitude Vegetation. I'll give a little bit of an introduction to why we're taking the approach that we're taking here. So my affiliation is with the Scott Polar Research Institute, which is part of the University of Cambridge. The material I will try to cover in this talk, I have quite a lot of material and not so much time, so maybe I won't manage to complete all of this program, but this is my synopsis. I want to start by talking about a little bit about what's so important about high-latitude vegetation. I think my colleague from Durham University, Bob Baxter, will say rather more about this probably. And then I will talk in a reasonably fundamental way about the kind of things that we can measure. I will start by focusing on the use of visible near-infrared remote sensing imagery, but then I will try to put that in the context of other sources of data that we can use. If I still have time, I will focus on a couple of the particular challenges that I think we face in using remote sensing data to look at northern vegetation, and then I will try to give an overview of what I think has changed in the last approximately 20 years, what we can do better now than we could do before. So I should give some acknowledgements. As I will explain in tomorrow's roundtable session, the work that we're currently doing is part of a collaboration, a UK-Russian collaboration. So I have many colleagues here in Moscow to whom I give thanks. I also have collaborations with institution in Norway. I should also acknowledge the support of the UK Foreign and Commonwealth Office International Fund and the Science and Innovation Network, which is responsible for the British presence at this conference, which we're very, very happy about. So, how does vegetation change as we move north? Obviously, we move progressively to places that are colder, less vegetated, have less organic material in the soil, fewer nutrients, more empty space to expand into, and more disturbance by ice. So we have fundamental changes in the nature of the vegetation. Crudely, we have the concept of a tree line. Line is not a very good geometric model for what we're describing here, but it's a convenient shorthand. Even if we adopt this shorthand for a tree line, an Arctic tree line, I think we can say there is not a universal agreement on where to draw that line. There's some quite big variation. So we should actually be talking about a transition region between boreal forest and what lies to the north of it, which is tundra vegetation. At the simplest level, we should expect that as a result of climate change, this zone, this transition region, should be moving northwards. A major control on the distribution of northern vegetation is climate. It's not the only control, but it's a major control. And the climate, we believe, is becoming warmer and becoming wetter. And these are both things that favor the growth of trees. So we would expect a northward advance of vegetation. We know, it's generally well accepted, that the climate has warmed over the last century, globally on average about 0.7 of a degree over the century, but as we already heard this morning, the warming has been greater at more northerly latitudes. It's maybe 2 to 3 times as big as that. So we have the increase in temperature over the 20th century. And this is modeled to continue and indeed to accelerate. We obviously have less secure knowledge about what the climate will look like at the end of this century than what it did look like a century ago, so the models are a bit uncertain. But broadly speaking, we expect warming, and we expect more warming in winter than in summer. We also expect an increase in precipitation. We expect especially the northern latitudes, to become wetter. And a warmer, wetter Arctic would be good for trees. So, if we put, and this is not fundamentally my research, actually this slide and the last several slides that I showed you are not derived from my research, it's just synthetic. But if we put together the information on what we expect to change in the climate with the most sophisticated models that we currently have about what vegetation should grow where in response to climate, we expect a northward shift of vegetation. This is not the most recent of the dynamic vegetation models, but it's typical of the kind of model that we expect to see. So if we compare between essentially now, 2010, it was 9 years ago, I suppose, and the end of the century, we expect to see a northern shift of vegetation distribution. What would this mean? Why would this be important? What would be the implications of a change from tundra to forest? Well, put very simply, trees are big and dark, and they've got a lot of biomass. 1 hectare of typical boreal forest has a mass of something like 200,000 tons. There's a lot of water and a lot of carbon stored in the forest. It's dark, it has a low albedo, it reflects rather little shortwave vegetation back into space. It's how the forest makes its living, essentially. On the other hand, by contrast, tundra plants are smaller, they're lighter, I mean they're more reflective. There is much less biomass contained within tundra. 1 hectare of tundra might have a mass of 10 tons rather than 200,000 tons. The storage of carbon and water is much less, and the ability to reflect shortwave radiation, sunlight, is much greater, so the albedo feedback looks completely different. So, if a lot of tundra turned into forest, as we said, compared with tundra, forest cycles huge amounts of water and carbon, reflects much less solar radiation back into space, represents completely different habitat. Those are the physical differences. What would the implications be? Well, we can think about this in terms of what's called radiative forcing. We can compare the effect of switching land cover from tundra to forest to the effect of changing other climate driving variables. So if we were to switch all of tundra vegetation into forest, I'm not saying that's going to happen, but if we were to do that, it would have roughly the same effect as doubling the amount of atmospheric carbon dioxide. Roughly the same effect as increasing the sun's power output by about 2%. So the potential here is enormous. It's actually very important indeed that we understand how tundra is switching to forest, how forest is changing, how forests are densifying and moving north. Some models, we're kind of stepping back from models that are this severe, but some models still predict that by the end of the century, up to 40% of the Arctic tundra could switch to forest. As I say, we think that's probably a big overestimate by now, but this is the extreme end of predictions. So, as we already heard this morning, remote sensing, Earth observation represents our best, probably only realistic way of studying high-latitude vegetation distribution in sufficient detail. And what are the kind of parameters that we can hope to study here? Well, if we take the Committee for Earth Observation Satellites Earth Observation Handbook, which, if you don't know it, I highly recommend to familiarise with. I've abstracted what the CEOS handbook says about the parameters that can be, vegetation parameters that can be measured from space, and I've reclassified them here. So there are about 10. We have land cover type, vegetation type, soil type. These essentially all come from the classification of images. We have vegetation index and leaf area index, above ground biomass, gross primary productivity, growing stock volume, these parameters. These are from algorithmic estimation, needing not just the images, but ancillary data of one kind or another. We have vegetation cover and canopy cover, which are sub-pixel statistical estimates of vegetation amount. And we have canopy height, so the first explicitly three-dimensional measure that we can potentially extract from remote sensing data. I won't cover all of these in the same level of detail. There isn't time to do that. But what I will try to do is take a increasingly complex view of what's possible to extract from data. So if we start with the simplest idea of all, how can we study vegetation from remote sensing, specifically northern vegetation? If we start with the simplest possible idea, visual inspection of imagery that looks like a photograph. So if we talk about true color imagery, this is a very familiar idea. It needs a fairly minimal level of training to engage with this as a technique. So here's a simple example. Two true color images, so the colors are natural, they are as the scene would look if we had the same vantage point as the satellite, we were in space observing the terrain. So it approximately corresponds to human vision. So we have very little difficulty in understanding an image like this. We've got a short time series here covering, 30 years. It's an area in the Hibini Mountains on the Kola Peninsula, which is very familiar to my colleagues in Moscow State University and me, because we've been working in this area for about that long, actually, since around 1990 or so. It's an interesting area because we've got both climate response and we've also got localized significant industrial impact in the area. So there are all sorts of dynamics that we can study, and they're not difficult to see in a comparison of images like this. We can take the same idea, visual inspection of imagery, but we can just one step away from the very familiar true color imagery into the false color infrared imagery. So this is, I'm sure, familiar to most people in the room here. So at the top left, a true color image, natural color, as you would see by human eye. Bottom left, we have, in fact, the same, so imagery from the same satellite system, but showing a different range of wavelengths, showing, including the near-infrared wavelength, to which the human eye is not sensitive, but most satellite systems, well, I'll classify them shortly. Many satellite systems are sensitive. And we immediately see, looking at comparing the bottom left image to the top left image, that the ability to discriminate subtle variations in the strength of the vegetation, the vigor of the vegetation is clearer in this image. And on the right, so the two images on the left are from Sentinel-2 imagery, which I think, Kevin, you're probably going to be talking quite a lot about Sentinel imagery in general. So, so this is kind of like Landsat, but a little bit different. The same, it occupies the same territory, essentially. On the right is it's another satellite image. It's a false color infrared image, but this is much higher spatial resolution. This is quickbird imagery, and at this level we're seeing individual trees and shrubs. So the point is that we are easily able to interpret just by eye, qualitatively, this kind of imagery. Okay, moving on to an area which I will try to expand here. We have a technique called we have a mathematical concept called the Normalized Difference Vegetation Index, NDVI, which I think is pretty familiar and I would say is one of the most useful ideas in the remote sensing of vegetation. So the image we're looking at here is, it's not an image, it's a global data set which has been compiled from actually from many images. It's a 16-day composite, so it's an almost snapshot covering half a month. Showing something which is in fact not exactly the NDVI, it's something called the EVI, which is another vegetation index very similar in context to the NDVI. You see the color scale along the bottom, and it's fairly clear that what we're looking at here looks a lot like a map of global forest. So why is that? Here's the definition of the Normalized Difference Vegetation Index. I think this is pretty well known as well. It's the difference between the reflectance in the near infrared. Can I point with this? Yes. The difference between the reflectance in the near infrared part of the spectrum and the red part of the spectrum divided by the sum. That's a mathematical peculiarity which just gives the definition some useful properties. It means that it's a number that ranges between -1 and +1. Formally, we can define this as a kind of image algebra. It's a mathematical operation performed on a remotely sensed image to generate what is in effect a new image. So, if we have a remote sensing system that gives us these two quantities, the red reflectance and the infrared reflectance, which they nearly all do, we can calculate this quantity. For example, if we're using data from Landsat 7, the enhanced thematic mapper on Landsat 7, we need what's called band 3, which is the red reflectance, and band 4, which is the near infrared reflectance. So we would alternatively write this equation like this to make it specific to the Landsat 7 sensor. So what this NDVI concept does fundamentally is it expresses how good a material is at reflecting infrared radiation, near infrared radiation, and how bad it is at reflecting red light. And that is very closely related to the quantity of green leaf vegetation present in whatever region of the Earth's surface the satellite sensor is looking at. We can see why that is in a couple of slides here. The Landsat 7 enhanced thematic mapper, I'm taking that as an example of a typical instrument that can be usefully used for this application. Essentially takes averages of the amount of, we shouldn't call it light because it goes beyond the visible spectrum, but I will approximately call it that, light and infrared radiation over a range of wavelengths. So here they are specifically for Landsat 7. We've got a scale of wavelengths along the bottom here ranging from 0.4 micrometers, 400 nanometers, which is in the blue part of the spectrum, maybe just in the ultraviolet, through green, into red, and into the near infrared part of the spectrum. And here, as a series of grey you think they're grey. Bands, we have the regions of sensitivity that the Landsat Enhanced Thematic Mapper instrument has to radiation. So it's averaging over this range. This is band 1, band 2, 3, 4, 5 and 7. Band 6 is over here in the thermal infrared somewhere. So here, underlying this graph are 3 reflectance spectra, as we would say. They're the fundamental units of this kind of remote sensing. So here we have this brown one. This is some soil or other. I don't know which particular kind it is. Here, this green curve is the one that we particularly want to look. Oops, that's not good. Thank you. This green one is the one we particularly want to look at here. This is a typical green leaf, or vegetation composed of typical green leaves. So we see it has a kind of low reflectance in the visible part of the spectrum, but not quite as low in the green part as in the blue part and the red part. So it's going to look green to our eyes. And then when we go into the infrared part of the spectrum, the reflectance suddenly jumps up and is much higher. And it's this contrast between the red reflectance here and the infrared reflectance here, which is the essence of what the NDVI does. So, why does this work, this NDVI idea? As I said, or as I've implied, it exploits one of the most characteristic spectral signatures in remote sensing, what things with green leaves do. So green leaves have high reflectance in the near-infrared part of the spectrum. So here's a very fussy graph with a lot of things we don't need to look at, and something we do need to look at, which is the thing labeled green vegetation here. So here's the high reflectance in the near-infrared and the low reflectance in the red part of the spectrum. And fundamentally, this is the physiology of the leaf that's controlling this. In the near-infrared part of the spectrum, the cell structure of the leaves is responsible for this high reflectance. Essentially, the infrared photons, they get into the cell structure here, they bounce around in the cell structure without being absorbed, and the chance is very high that the photon will come back out again. So there's a high reflectance. In the red part of the spectrum, something completely different happens because of the presence of pigment called, well, there are lots of pigments, but the one that's really important here is chlorophyll. And that sucks the red light and the blue light out of the radiation. So, high values of the NDVI are telling us that the material we're looking at is good at bouncing out infrared photons and good at absorbing red light photons, and that's a thing that green leaves do. So there is a strong association between NDVI, which is a mathematical thing we can calculate from an image with the right imaging properties, and a concept which I'll define on, I think it's the next slide, I hope it's the next slide, the leaf area index. And this is our link from the mathematics of what's present in an image to something which is physiologically useful. Just while it's there, it's rather small, but just to notice right at the bottom right of the slide here, there are 3 little cartoons, they're not my cartoons, of the differences between the optical and infrared properties of normal green leaves and abnormal green leaves. So here we have a normal, healthy green leaf, which is really good at reflecting near-infrared radiation and really good at absorbing, so not reflecting red, and the other colours are included here. Here's a leaf that's undergoing stress. It's chlorotic. It's turning yellow. And here's a leaf that's so stressed that it's died. And you can see there are fundamental physiological changes in the leaves here. The cell structure breaks down, the amount of chlorophyll decreases as well. So both of these things shift the relative amounts of near-infrared and red radiation that will be reflected by the leaf. So this is picked up in the index as well. So this is extremely useful. So this leads on to the idea of the leaf area index. And this is an important physical characterization of plant canopies. Sergei mentioned it. more than mentioned it actually. And it's one of the most important links between remote sensing Earth observation and, as I would say it, I have to do a lot of teaching in a geography department, and biogeography. How the concept is defined, it's slightly different depending on whether we're talking about broadleafed vegetation or needle-leaf vegetation. For broadleaf vegetation, it's really obvious. Leaves are flat things. They have an area you can measure. You can put it down on a piece of paper and trace around it and measure the area. So a leaf has an area. It's got two sides, so it has two areas. It's one side. So it's the one-sided green leaf area per unit ground surface area. So we imagine taking a quadrat, but probably a really big quadrat, maybe a 1 hectare quadrat, and we go all the way through the forest canopy, and we count the area of all the leaves in that canopy, and we divide that area by the area of the ground, and we get a number. It's just a ratio. And that is the leaf area index. For needle leaf trees is a little bit different, and there are slightly different variations, but they basically do the same thing. So it's unitless. It's strongly correlated with productivity. We would expect that because the leaves are where the plants do the producing. So it's telling us how much of the growth engine is present in the plant. And it's therefore strongly correlated with the NDVI. So as I say, this is our link. But the relationship's not a linear relationship, and it saturates. So if there's a lot of leaves, the relationship becomes less sensitive. So there's a couple of things to say about this relationship. One is that it saturates, and the other is that we are less certain about the relationship between NDVI and leaf area index for boreal vegetation than we are for more temperate vegetation. So here's an example. It's actually not for forest at all. It's for agricultural crops in France, but it shows a typical relationship. Here is the leaf area, sorry, it's in French. Here's the leaf area index. Here is the NDVI. Here is the relationship that is monotonic but starts to saturate. So when the leaf area index becomes higher, the amount of change you get in the vegetation index gets smaller. We can understand that fundamentally. That's what these graphs, which have come from our joint work, is telling us here. We've got, if we imagine just making a stack of leaves, just piling one leaf on top of another, 1, 2, 3, 4, maybe 10. How does that change the reflectance of the stack of leaves in the visible part of the spectrum? That's what the green dots show. And in the infrared part of the spectrum, that's what the red dots show. It changes the infrared part quite a lot because leaves are actually quite a lot transparent in the infrared part of the spectrum. But in the visible part of the spectrum, it doesn't change it very much because leaves are fairly opaque in the visible part of the spectrum. Take a leaf off a tree and try and look through it. Some light comes through, but not a lot. If we had infrared sensitive eyes, we'd see quite a lot through the leaf. So here's an example of that. This is, again, kind of familiar stuff, I think, quite typical. This is a true color image. It's Sentinel-2 imagery from just about 2 weeks ago, 3 weeks ago. This is the area around Montragorsk on the Kola Peninsula. Here is the corresponding NDVI image with a color table applied to it. And we've got typical values of NDVI, which are small and positive for tundra vegetation, which are between 0.3 and 0.4 for the boreal forest vegetation here, and some rather interesting areas, if you're interested in industrial impacts, what we call technogenic barrens, areas which have been turned vegetation-free as a result of industrial emissions, which are around zero. And water areas which are a little bit negative. So NDVI on its own, just a mathematical technique, but actually gives us a lot of information about how vegetation is distributed. We can estimate leaf area index from NDVI. This is not our work. As I said, it's a dimensionless ratio, so It can be measured like this, square meters per square meter. So this is what the global distribution of leaf area index looks like, from values below 0.5 in deserts up to in the densest forest areas. So we're looking at equatorial forests where it can be 6, 7, something like that. In the boreal forest, we're 1, 2, something like that. This is what Sergei was talking about in detail, so I'm glad I don't have to cover this in detail. That's very helpful. Algorithmically, we can estimate plant biomass, above ground biomass, woody biomass, growing stock volume from leaf area index. This is, again, this is not our work, but here's an example of that. So we've got above ground biomass, tons per hectare for Sweden, as it happens in this particular case. Sergei also talked about phenology. Phenology is something that the use of the NDVI is particularly skillful at tracking, especially if we've got deciduous vegetation present. Here is a set of NDVI time series ranging from winter, December, through summer, June, July, August, back to winter again, for actually 3 different latitude ranges. So we see the phenological variation, we see winter, spring, summer, peak greenness, and back to autumn and winter again. Once we have the ability to do this, we can track phenology over time, we can date the onset of spring, we can date the onset of autumn, we can subtract one from the other and establish the length of the summer. We can do this as a time series and investigate the rate of change of these parameters. So here again, it's not our work, it's Zeng et al. Here are changes between 2000 and 2010. In the northern hemisphere. So this blue color here is showing us areas where spring became earlier. This red color here is showing us areas where autumn became later, and this red area here is showing us areas where summer became longer. The changes that we would expect to see as a consequence of climate change, in a simple way of thinking about it. Okay, so I will mention the Greening of the Arctic NASA project, which takes this idea, time series of, this is not phenology, this is just peak greenness, but this is a nearly 30-year time series illustrating where vegetation index has strengthened, so where the Arctic has become greener, which is in most parts. This is just Canada, of course, and where it's become less, so a few areas where the Arctic has browned rather than greened. In places where it's increased, the main changes are that grassy tundra areas have transformed into scrub and shrub tundras have expanded and become denser. This one I think I will skip through quite quickly because I'm constrained for time, but let me just say that a major use of NDVI is studying pollution impacted areas, which are surprisingly common in the Arctic and subarctic region. It's some of our work, but I'll jump past it. Let me say this, can we always trust the NDVI? Well, obviously not, otherwise I wouldn't have this slide. When can't we trust it? Vegetation canopies may not be composed of leaves or needles, so the fundamental assumption about the relationship between NDVI and amount of vegetation may not always be true. Even if it is, the implied presence of a high leaf area index may be misleading. Sergei, you talked about this actually when you were talking about fire regeneration. Burn a forest, the NDVI and the leaf area index will drop dramatically. What happens next as the succession starts? things with leaves start to reappear. It may not be telling us that we have a healthy, normal ecosystem that's regenerated. We may get a misleading signal there. So we may get a pathological response to an extreme situation. We get grass or shrub regrowth, or indeed birch regrowth after disturbance. So what was a pine forest may turn into a birch forest. Or we may get shrubs pretending to be trees. Okay, I think, yes, I'm all right for time. So leaving the NDVI for the moment, I'll come back to it later. I just want to say something quite quickly about multispectral classification. This is quite well known, so I'll skip over it quite quickly. It takes the idea of the spectral signature and extracts more information from it. The NDVI takes two simple but important pieces of information from the spectrum and capitalizes on those because of the strong physiological link. The idea of multispectral classification is broader than that. It depends on the assumption that what we can call interestingly different surface materials, so surface variations of interest to our research, will have different spectral signatures. And that was kind of implied by a graph like this one that I showed before. So again, we've got the range of wavelengths from blue, green, red into the infrared. We've got amount of reflection going on here, and here a very busy slide, all sorts of different surface materials. And the point is that things that are physically different, in this slide anyway, have different curves. So if we can recognize these differences in sufficiently detailed satellite imagery, we can recognize the difference between materials. This is the fundamental idea of multispectral classification. So on the plus side, there's often a direct link between important physical or physiological or both properties of the material and some feature in the reflectance spectrum. We already know that for green leaves. On the negative side, we have imperfect information about this from our satellite data. The reflectance spectrum is imperfectly realized because we have discrete sampling of wavelength ranges. We have mixed pixels. We always have mixed pixels. So what's in one pixel is always a mixture of materials at some scale or other. Also, we make our observations, if they're satellite observations, from outside the Earth's atmosphere, and the Earth's atmosphere changes what we see in ways that we need to correct for and may not completely know. This slide doesn't fit on the slide. This is textbook stuff. This is the difference between the two main ways of doing multispectral classification, so I won't talk about that. As I said, we focus our attention on interestingly different spectral responses. So what are the reasons why we could have interestingly different variations? I've already mentioned stress and disease in vegetation. So here is some chlorosis on a leaf. It's a home oak leaf, I think. It's going yellow. Actually, bits of it are going red because the chlorophyll's died. We have phenology. Here is some spectacular phenology. We have things happening at different seasons of the year as the leaves finish their job. And of course, we have the fundamental one, which is differences in species and age, giving differences in color to which our instruments can respond. So a typical multispectral classification, probably most people in the room have done this. Here we have a true color infrared image, and of course we have some other spectral channels of data that we're not seeing in this image. Here we have a typical classified image. So the image has been processed using the principles of multispectral classification to generalize it. So there are, in principle, many millions of possible values that any pixel in this image can take, but in this image there are only 20 possible values because the image analyst specified 20 things. Mathematically, every pixel has been assigned to one of a limited, a defined number of choices. We've generalized the image. In fact, it's not an image anymore, it's a map. It's a map because every point on the surface has had a decision imposed on it. So we're making maps when we do this. Working out what the legend to the map is, maybe not straightforward. We can think of it as a kind of spatial extrapolation using training data. So we know what is present on the Earth's surface in some area because we went there, we did the field work. We've extrapolated using the image data to a wider range. Okay, I won't say about that. It's not very interesting. Briefly, let me say, not all classification has to be multispectral. We can include as well or use exclusively spatial information, so we can use texture-based classification. We can combine texture and spatial data too. Right. Taking a step back, what fundamentally can we do from space? We'll stay focused on space-based observations for now. We have some limitations fundamentally imposed on us by the atmosphere. The Earth's atmosphere is not uniformly transparent. Here's a kind of cartoon way of looking at that. This is a much bigger range of wavelengths now than we looked at before. This goes all the way from pretty far into the ultraviolet, through the bit we were talking about before, which is just here, into the thermal infrared, millimeter wave, and then out into the microwave part of the spectrum. The black parts of this diagram are where the atmosphere is opaque, the white parts are where it's transparent, and the kind of grey parts are where it's something between the two. And if you squint at this diagram, so if you defocus your eyes a bit, it's got three broadly transparent parts. This one, which is where we've been till now, the visible and near infrared. This one, it's a bit messy. This is the thermal infrared part of the spectrum. And then this one over here, which is the microwave part of the spectrum. And this threefold division of the atmospheric transparency gives a convenient way of thinking about the range of possible satellite-based techniques. That's a more complicated version of that diagram, which we won't use. So here they are. This is the visible and near infrared, the thermal infrared, and the microwave. This other way of classifying systems, of remote sensing systems, is based on whether they're passive, so they detect radiation which is present in any way, or active, so they actually illuminate, so they provide radiation and then measure what is returned. And that can either be in a simple way, just measuring the time it takes a pulse of radiation to come back, or actually analyzing the strength of the radiation as in an imaging technique. So this is a kind of taxonomy of all possible remote sensing, spaceborne remote sensing systems. Not all the boxes are equally usefully occupied, and I'm only going to talk about the red ones anyway, and we've already been talking about these. These are the visible and infrared images. But I also want to talk about, I also want to talk about what's in this box here, and a little bit about what's in this box here. I won't say too much about the Sentinel imager here. This is perhaps a useful way of thinking about the visible and near infrared sensors. We've got spatial resolution, so roughly speaking the pixel size, on this axis here, and we've got swath width, so the strip of Earth's surface imaged by the instrument on this axis here. And I've been talking about the Landsat 7 instrument, which I can't immediately find on this diagram, but here is the Landsat 8 instrument, which is quite similar. Here is the Sentinel-2 instrument. These are quite small pixels and quite wide swaths, which means they're made of quite a lot of pixels. So there's quite a lot of data involved with these. The point about this diagram is that there is a whole zoo of different flavors. Sorry, I'm mixing my metaphors now. There's a whole range of different approaches to Earth observation here, all of which have their particular advantages and of course disadvantages. And we've just been talking about this bit of the diagram here. Okay, so I want to talk a bit about airborne laser profiling and then about spaceborne laser profiling. This is a very simple idea in principle. We bounce a pulse of laser radiation vertically downwards or approximately vertically downwards, measure the time of travel and use that to infer the geometry of what we just looked at. So this can be done from an aircraft. It is often done from aircraft which carry a laser, an accurate laser, which is scanned around by a mirror and bounces pulses. How am I doing for time, Sergey? 3 minutes. Okay, right. Okay. In that case, let me just quickly show an example of visualized terrain from this kind of instrument. We see terrain, we can actually see vegetation in it. Three-dimensional structure we can measure from laser profilers because we measure the time of first pulse and last pulse, so we learn about the canopy. We can do this from space, but in a rather limited way because we have a rather finite network of tracks that we can obtain data from, and it makes mistakes as well. Here is a transect through the Hibini Mountains. Here is the terrain. Here is the inferred canopy height, which is obviously not really more than 100 meters in places. That's algorithm failure. Radar imagery I probably won't say. Okay, I only have 3 minutes, so I'm actually going to finish by talking about two problems and what we can do about them. The boreal forest intrinsically is somewhere where the vegetation cover is starting to become quite thin. So we have sparse tree cover. We have the danger that we can confuse the field layer with the canopy. Here's an extreme example of that danger. This is Betula pubescens, downy birch, in Norway. Its spectral properties are dominated by the leaves, which are kind of dark green. Here is dwarf shrub vegetation, Betula nana. It grows this high. The optical properties of the leaves are very similar to those of the birch leaves. So to a satellite, these look the same. In terms of biomass, they are extremely different. How do we deal with this problem? I'll tell you the short answer, because I now only have 1 minute. We have two ways out of this problem. One is higher spatial resolution, the other is higher spectral resolution. Higher spectral resolution we achieve with hyperspectral data, which we do not currently have the ability to collect from space. That has been possible in the past. It will be possible in the future, but at the moment we are limited to collecting hyperspectral data from field measurements and airborne measurements. Higher spatial resolution, we have some possibilities to collect from space, but again, we rely primarily on airborne and field level data. So the one, I wonder if I can jump, yes, okay, I can make this my last slide. How do we bridge the gap between field measurements and satellite images? I think the answer right now to this is, or a big part of the answer to this is drones, unmanned aerial vehicles. So the collaborative work that I will describe in the roundtable tomorrow, working on the Russian boreal forest, makes extensive use of data collected from UAVs, which is providing a very powerful way, we are discovering, of bridging the gap between field scale measurements and satellite scale measurements. So I think I've run out of time, and I will make that my last slide. I've got about 20 more, but I won't show them. So thank you for your attention.
Hello, Gareth. You said that 1 square meter of boreal forest weighs about 20 times more than 1 square meter of tundra. And so, as I guess, it consumes about 20 times more carbon dioxide from atmosphere. However, according to the forecast, which you mentioned, the carbon dioxide in atmosphere will increase about twice if, if all tundra turns into boreal forests. So, can we say that actually the impact of the boreal forest into the global carbon cycle is negligible and everything depends on the ocean?
I might hand that question over to Bob. I don't think we can conclude that. I think the ratio is more than 20. I'd have to go back to my slide. It's more like 200 or 2,000, I think, actually. But
even more.
I think part of the answer to your question is about timescale. And one of the things that we've been focusing our attention on is the extent to which the northward advance of vegetation is capable of remaining in equilibrium with changing climate. And actually, I think that's probably where the dynamic vegetation models are getting things wrong, because they assume it can and it can't, unless the terrain is actually quite steeply sloping. But I think Bob is more of an expert on this than I am. No, all right, he's not disagreeing. So, good.
Thank you.
I'd like to ask you a brief question about the classification slide. What was the reason to split water into 5 classes? Why is that?
Let me jump back, if I can jump back quickly enough. Not this one. This one, this one, this one. Yes. The reason this is the Pechora River, and it carries. This is the Nenets Okrug, Pechora Delta, Pechora River. And the main reason for needing so many water classes here is the amount of sediment being brought down by the river. So there are strong variations in surface reflectance, which is not so much differences in the type of sediment, but the depth to which it's being carried, actually. So this is largely a map of depth of the bay here, in fact. So we could have classified it in that way if we were more interested in hydrology than we are.
Thank you.
Спасибо. Thank you very much.
Okay.